Please take it away.
All right. So I'm Josselyn with Linkan Engineering. I just want to start off saying that I'm not the genius. I'm a more practical guy. My job is really to take the genius of other folks and make it practical, make it work in the field. So I'm actually taking one of Jim's presentations, and I'm going to kind of guide you through it in the way I kind of understand things. Okay, so for some of you, I'm going to be shooting low, but for some of you, hopefully, maybe I bring a new perspective so that you can kind of understand it like I do and make it more practical so that we can apply it in the field. So what is this about? So source control, you've heard it numerous times, and you're going to hear it again. We're going to say it multiple times. And what this program is kind of about is the fact that we're at a crossroads for treatment right now. We're at a crossroads. And what am I going to do for treatment? Well, I want us to take a step backwards. And let's go back and figure out why we're doing the treatment. And let's look there at maybe where the solution might be. So we can stop doing it, or at least minimize the amount of treatment we do. So I'm going to start going through just some preliminary things about source control, especially for ARD, and why we're focusing kind of just on a particular target to attack it. And then I'm going to go into a very project-specific, where we are actually kind of going down through some test protocols to come out with what specifically will work at a specific site. So, I guess, why are we doing this? What is this all really about? And we see here, we've got definitely some mine, woods, water here, and it was from there, right? And we want to treat this, or we want to maybe try to return it back. So one vision I want you to take here is that source control is pollution prevention. So we want to prevent it so we don't have to treat it, right? And but I really want you to have the visualization that we want to maybe return it to the way it was in a natural state. So we wanted to return it back to its regular ecosystem, where this wasn't pouring out of the mountainside, right? It took millions and millions of years. Certainly this happened when this mountain first turned this thing up, right? All the pyrite was exposed, and we had it. It took millions of years to resolve it. But we don't have millions of years, so we got to resolve it quickly. This is a little slide. So really, so ARD. What are the sources of ARD? So I need a reference, right? So if you think back in your schooling time, there's this whole concept of this fire triangle, fire tetrahedron, because they ultimately figured out that they could extinguish this thing if they could get rid of the chemical chain reaction and not get rid of the fuel, the oxygen, and the heat. So like halon was a great example. I couldn't explain how it worked until they came up with the fact that it disrupted this chemical chain reaction. Well, ARD is a lot like this. It's a tetrahedron. You can knock out one of these legs, you can knock it out. And for a long time, this fuel was pyrite. And then if you mix a little water, a little air, or another oxidizer, you have ARD. But what was lesser known was the fact that this bacteria that greatly accelerate this process. So they're really kind of the chemical chain reaction that is occurring there. So we want to focus on that. And so think of it, and we have this huge epidemic out there. We have kind of a disease, a virus, all these bacteria out there. Excuse the football there. And it's impacting all this mine water. And it's insulting it and changing it. And we need to do something about this, because treating it is maybe forever. So source control is very practical if we can do it. So let's go back to our tetrahedron. Again, you can knock off any one of these things, and if you don't, then you may have something that's going to take millions of years to resolve, and it wants to do that. So why do we think it will work? Because it has. I mean, there's actually quite a few cases where we can show where adding a bactericide has ultimately proven to take the site to remediation. And I'm not going to go into that because it's too music that you're standing right up here last year. And so we gave you a reference, and he's on YouTube. You can just look that up, and we'll go through quite a few of these examples. And a lot of them are just kind of forgotten sites now, and that's really the cool thing. That if you ask the EPA in that area about that mine site, they go, what? It's because it's just not there. It's not contributing to ARD anymore. So, again, talking about knocking off the legs for the ARDs, the source control, you can do various things. And most of that work has all been done on, well, you can't really do much about the wastewater. I guess you can find somewhere else that might do that. You can take away the water, and by covering it, making it high and dry. You can get rid of the oxidizer by basically putting it under water. Again, making it high and dry and covered, remove the oxygen. But we're mainly just focused here on this chemical chain reaction here, the bactericide. So, bacteria. Let's go in a little bit into this bad bug that we have. And they're all over the place. Like I said, it's really kind of an infestation. They've taken over. And they increase this ARD rate exponentially. So if you didn't have it, you had a pile of pyrite out there, and just water and air without the bacteria, you might see a slight change in pH and almost no metals load. Add the bacteria, and you have very significant pH reduction and very high metals load. So, it's important. And then, anyway, it's been found in neutral water, which is really evidence of what has happened. And maybe that's an alkalinity influence to it, and so now it's more neutral. So I want you to think about this bug not as this ferocious monster. It's not out there, it's not a killer beast. It's really more like a skunk. It's kind of cute. But it has a way of changing the environment to exclude all others. So if you let too many of them get out there, they can exclude all others. And so they change the environment. So think of it more, it's not a ferocious thing, but if you let it, it'll take over. I don't know that skunks are taking over the world, but you can imagine it would really stink if they did. So how do we do this source control for the bacteria? One thought is just apply bactericide, right? And you can devastate them. And just like in those Lysol commercials, where they wipe the counter clean and then they show you a little circle and there's still 1 or 2 bacteria, you can't remove them entirely. You can decimate them, but you can't remove them entirely, so they come back, right? So you have to create an environment, if you do decimate them, first, where you can keep them from coming back. Unless you want to retreat again and again and again. You don't want to do that. That's kind of why we talk about source control and returning the environment back to the way it was. That's ultimately the goal here. Well, so we have another weapon now. And this helps us get back to an environment that was more natural. And it's actually using milk. And what it does is it also can decimate the bad bugs by isolating them away from their food source. It can coat pyrite. In fact, it's kind of maybe a heat-seeking missile in some respects, a smart weapon, because when it reaches an acidic change, it actually forms cheese. And then this cheese coats the pyrite particles, and then it keeps the acidophiles from getting to it. It keeps the water in the air from getting to it. But who loves cheese more than bacteria? But good bacteria. Cheese brings in the good bacteria. So now we've got 2 things going. We can kind of decimate the acidophiles and bring in the good bacteria. Just try one. So don't throw that bad milk down the drain. So anyway, that's just kind of my primer on source control on the bacteria side for the ARD. So I want to get into this project. So this might seem somewhat similar to some other projects. Other than this was in South Carolina. There was some historic mining back in the 1800s, and that's followed on with a lot more active, kind of aggressive mining later on in the 1990s. They built a big pit, and they did a bunch of processing, and then the economics kind of turned on them, right? And so they decided to close, use some of the money that they had to start doing some remediation, but ultimately they go to bankruptcy. And then about 7 years later, they had an emergency situation because the infrastructure was bad and they had really ugly water there. It was outraged with bad environment. So there was emergency action then in 2007 to take care of some of those issues, and then a supervital designation. So here's the site, right at the precipice of the emergency. And they have, like I said, a lot of failing infrastructure here. They have a hit lake. So it's a pH, 1.5 to 2.2, and it had no spillway. So if it started spilling, it's going to basically erode away walls, and you're going to have big, massive water coming down the valley. They had a whole bunch of infrastructure problems there, and also a bunch of participating mine waste, or just a mine rock pile. We don't want to talk waste. So they did start working up there on some of this emergency work. They put in a spillway, and they started treating this pit. This pit, again, pH is really low. So they actually were adding a whole bunch of lime to it and added a bunch of carbon sources and trying to almost kind of make a BCR out of it, a big BCR. And they also were trying to deal with all this waste rock, the stockpile material, and they've done as much of it they could of it in the pit. It submerges to keep the air away so that it can't be contributing to ERD anymore. But there was no way they could put it all in there. So then they put up caps on the top of it, and so this area is capped now, and then this area here. And so now this is 2016, and hey, we're looking pretty good. I mean, it's vegetated. The watercolor, I think, maybe is a little better. And so, I mean, what's the problem? Well, the problem is we really haven't. We made it look nicer in an aerial photo, but we haven't handled this pit lake yet. It's still very low, and the water still rises, and it can still spill. So we really haven't got to the crux of the problem yet. Then after multiple, there's a problem. We've neutralized this pit multiple times, but it doesn't stick. And it's really because we haven't gotten to the source. We're treating the water here by neutralizing the pit. And where is the energy coming from? It's not coming from the pit. It's really coming from this pile, or almost certain of it. And it's valley from, right? So, and actually, we do a really good job of diverting water. So it has a bunch of water flowing over it. There's high precipitation in this area. We've got water coming down on the top of it, and there's a whole bunch of pyrolysis. So this is where this project kind of started, through the EPA at Fairlight Hill. And it was really just the first phase, proof of principle testing. So we're just trying to go out there and show that some ARD suppressant would work. And just to the point where we can say, yeah, we should test this further, not for field application. So it's just proof of principle testing. So how do we kind of go about this? Again, this is really kind of, we're getting to the point of having enough data that we can quickly look at it and spark it. Okay? So it's not about how good it looks, maybe how good the data looks. And we can say, yes, this technology we want to carry forward, or no, we're going to eliminate this technology. So first we just wanted to do some simple tests just to look at somehow we're going to use some of these amendments, this sodium lauryl sulfate, the bactericide, or milk, and alkalinity, and how did it react? How much do we need to use? And from that, we can maybe remove some of those right away with just some preliminary testing. And we use this ASTM method that shows what the field capacity is and then how much stays after rinsing a while, because we need something that will stay liquid for a while, just when rinsed out instantly. And then, and so we actually did a bunch of feasibility kind of testing on some other things, but we're really going to focus here on the waste rock stockpile. So again, this is proof of principle. So in proof of principle testing, we're not doing a lot of divisions on the concentration. We're trying to figure out a concentration that will work. Maybe add 50% more. Amendments are added in excess. And we're just trying to figure out which amendments were the most practical to use in the next phase of testing. That's what we're doing. So again, it's really kind of going to the level of swipe right. Or left. So go. I think maybe that's an EPA. So anyway, so we had a couple discoveries when we went out there. First, we had to go get some of this material, right? So we went out there and excavated through the cover material down into the waste rock. And one thing that we found here was that it was really super fine, some of these particles. And actually, we had a lot of problems with this because we couldn't get any permeability. And certainly there is some, but we can't deal with this in a short lab test if we can't get water through it. So we had to come up with a solution to that. The other thing we found out was extremely dry. So at least in the 3 places that we disrupted the cap, we're not so certain that there is any infiltration in this cap. So the cap seems to be really working well. So basically kind of cutting out some of our theories, some of that maybe adaptive management we were talking about, it was coming to play here because the results that we were finding were developing how they were going to proceed to the next level of testing, the tier 2 testing. So anyway, I just want to go over, to handle the permeability problem. If we just put this material in our test buckets the way it was, we can't get water from it, at least not fast enough for our satisfaction to run this test. We can't run it forever. It's just not enough money to do that. So we agglomerated. We basically add a little water, rotate it around, the little particles stick to the big particles, and basically create some void space, gives us some permeability so that we can run these tests. Later, we're kind of wondering about some of the validity of that, but that's what we have to do to get these tests done. I want to talk about the conceptual site model here, because we have 3 basic zones that can all produce ARD. And you have the unsaturated zone. And we want to illustrate this. They actually had some leftover liners, so they threw it in a couple places in the cap. We just really didn't want to excavate right here, because we assume that was impervious there. We have this unsaturated zone, we have a transition zone. And there's kind of a tide on the ground that's happening where the water level rises and falls. And certainly we feel like this is a real target area for ARD production because it obviously has lots of water, a lot of moisture, and air. Because it's, as the water fluctuates, it's actually sucking air into the system there. And then we have our saturated zone. And we don't worry too much about that because if it's submerged, it's always submerged. But if these above zones are contributing ferric iron, the ferric iron can come down in here and be deoxidized. It creates more ARD. So we do care about the saturated zone. So again, I'm going to go through kind of what we did for each one of these zones. The unsaturated zone, we feel that if there's water infiltrating in, there's certainly some air that can also infiltrate in. There's plenty of pyrite there, and so we care about both the residual acidity that might already be there, where pyrite's already been converted, but it didn't have the water to move, so it's still there ready to move. And then plus just to be able to create carbon from the fresh pyrite. So it's just residual versus stored acidity, and then potential to create more acidity. So in this test, basically, we're using 5 gallon buckets testing here. We put the media in, and then we basically just kind of simulate the field. We would kind of flood the media and then basically drain it. And then we would test this media on a weekly basis. So that was kind of our unsaturated test method. We had control cell, of course. We had SLS with alkalinity, without alkalinity, and then milk, with or without alkalinity for all these tests. We're trying to get the environment to change, so we want to really good ones. So we want to source for those. This is just kind of data. The test was run for 14 weeks, and we can see how automatically those that had alkalinity made a quick adjustment to pH right away, as you would expect, right? In fact, we came up with the amount of alkalinity based on some jar tests that tells us how much to bring the pH right up. So over time, we want to see what happened here. Would they totally diminish and go down to where the control was, or would they potentially level out? And fortunately, this was a 14-week experiment. Again, this is a no-no-go. So that's as far as we could run, and we don't know. It definitely looked like the data was leveling out for us. But milk obviously shows here that it has something significant over the control data. So the other part of this that we really wanted to look at is the bacteria, because that's what we care about here. What are we doing with these populations? So this was really kind of one of our big decision points, whether we're going to swipe right or not. So we were doing kind of bacterial counts. And we did two different types. We did basically bad bacteria counts and good bacteria counts, because we want the bad bacteria to be decimated, right? And we want the good bacteria to start growing like crazy. So we were looking at this. So this was, like I said, a big part of our decision factor, whether this technology should be carried forward as a method support. And the clear winner here was SLS, the bacteria side of Agglomeration, because as far as bad bacteria, they really decimated them hard, and they had a hard time coming back in that quarantine test. So that was kind of the one winner. Although we have some other winners here. So really, in this phase of testing, we would have one higher recommendation and a few others that we would keep on the list and see if we get some good filters later. So anyway, I'm talking about the transition zone. Here, again, this is where we think, especially now that we know that this material is really, really dry, not very permeable, that most of our water that's flowing through the system is probably coming through the transition zone. And sure enough, there's a whole creek upstream that just kind of disappears. It's not diverted. It has to go through the bottom. So, of course, that's one of the solutions to divert that. But we know we want to test this transition zone here. And we don't know how thick it is. We think it's only a couple of feet thick, but it could be a major source of our ARD. And finding out where the RD is coming from is very important, because we need to be able to target the solution. You can't just apply SLS everywhere or milk everywhere. It's just not an endless supply. So here, again, we had an SLS with alkalinity, milk alone, milk without alkalinity and control. And in this case, what we did was we flooded the cells for the whole week, and then we let the water level drop for a whole week. So again, we're trying to imitate that and just use weekly cycles. They're probably seasonal cycles, but we have 14 weeks. So we did weekly cycles to come up with a kind of simulate what was happening in this transition zone. And here, we got some of our best results. Again, with those that had alkalinity added, we had an initial pH spike, and then it started heading downhill and perhaps leveling out. But here's where milk really kind of showed through, because the pH kept improving week to week in the transition zone. And again, our controls, one thing that was really nice about this test, and it doesn't always happen, is our controls were super consistent. They were back. And so here, again, just looking at we're looking at good bacteria. No, we're looking at that. Here we're looking at good bacteria. And the milk and alkalinity here really showed that we can spur out a population of good bacteria on this test. So this is a saturated zone. Again, not if we can control these two zones, especially the transition zone, we shouldn't have a problem here. We want to make that part of our test, because there are how these amendments might impact that zone. But we only did it with milk. It looked like it might be the winner. And some of our preliminary tests kind of excluded SLS and didn't want to do anything down there. So we just went with milk and alkalinity to show what that might impact the saturated zone. We basically just kept this flooded all the time. We put water in the top and then take water off the bottom, so it's completely saturated throughout the test. And here, again, mysteries of milk. So that was greatly improving the pH of this test, more so than just alkalinity alone. So here's where we're able to show that milk is kicking something else in to the test. So again, just looking now at good bugs, again, the milk with alkalinity, we can see, just alkalinity alone, we're not adding to the bacterial population of good bugs. But with the milk, we definitely are. So this was a really good result. So our big conclusion is, hey, source control works. At least at the proof of principle level for this site. And so we had quite a few swipe rights in this. So hey, we're gonna see if the chemistry works later on this. And so our big conclusion is that we can adjust the microbial community. We're able to decimate the bad bugs, bring in the good bugs. So that worked really well. That SLS with Alkalinity, that worked in 2 of the zones really well. Milk with Alkalinity worked in 2 zones really well. So certainly those 2 can carry on to the next phase of testing, kind of the tier 2 testing. And then also, we think maybe that adding bactericide within milk was a good idea. It wasn't really a good idea because ultimately that bactericide, unless you let it fully dissipate, also takes out the good bugs. So that was a good test because it didn't work well. So we progressed from our rate of failures. So of course the next step to talk about that is really tier 2 testing. We're actually kind of negotiating right now at the site to go to the next level of testing. And this is where we'll kind of fine-tune exactly what type of concentrations we're going to use to be most effective. And how we're going to apply it, that's a big thing. On all this testing, we didn't do anything for how we would apply it. So now, part of tier 2 is to go out there and figure out the right concentration. You don't want to turn the whole pit lake into a big, foaming lake, right? So you can't overdo the surfactant. And you don't want to overbite the milk either. So we have to figure out, dial in the concentrations, and then figure out ultimately how we're going to apply it to some pilot tests. So anyway, I want to pull this up real quick. We're doing quite a bit of the same work here locally of the Yankee tunnel, and it's hard to see in this photo. Actually, went out there yesterday, and it was already dark by the time I got there, so it was a little But anyway, this is we're basically kind of going through the same process to figure out which amendments will work, because it is site-specific. And it's just some people to work with. I do want to point out that really, we were doing it through a subcontract, and Renke Dawkins was a huge help with Black and Beach, just went out of his way to help us out on this project. And anyway, this is really one of Jim's slides, but it kind of hits on. Who did you start with? Jim's still here? Yeah. Yeah. Sodium bicarbonate. Sodium bicarbonate.
Thank you so much.
Yes.
Kind of curious, this milk, being an organic substance, how long does it last? Is this a problem? Longevity in the ground, stuff, whatever?
So it's not going to last forever. In fact, that's one of the good things about it is because it starts getting eaten up by good bacteria. The thing is, we want to follow up with vegetation. Because ultimately, vegetation is the key. And humic acids from vegetation then actually become the bactericide and the kind of food for the good bacteria. So milk helps set the stage, but it's not ultimately the answer. Although Jim's got a beaker on his desk. It's been there for years. It has milk in it, and it's still there today. So it's a cheese ball that just won't go away.
Cheese ball or smell?